This example problem deals with centripetal force in a situation where a car is on a banked curve, going around a curve, and the curve is inclined to the horizontal, and we're in a situation where there's ice on the road. The roadway engineers are planning for a situation where it's icy, and we want to let the cars go around at 40 miles an hour and stay on the curve. Stay on the curve at 40 miles an hour. Not responsible for going faster or slower than 40 miles an hour. We'll talk about that later. The curve has a radius of 500 feet, so the car is going to be moving around on a circle with a radius of 500 feet. We don't know the mass of the car. But let's think about this first a little bit. We've made a drawing here, got a drawing with an incline and showing the weight downward, and the weight has some components to it. There's a component of the weight that presses into the incline, that's mg cosine theta. The adjacent side to the angle, we use cosine theta to do the calculation of the component, and the side that's opposite to our angle theta at the top of this triangle, mg sine theta, is this component of the weight that's parallel to the plane. The angle theta is here. You might want to pause and convince yourself that I've put theta in the proper position. Do some right triangles. There's a right angle here that you can make use of. There's a right angle up here you can make use of. But the angle at the top of this triangle will always be the same as the angle of the plane. So what's going to happen to the car if we just place it on the roadway? It's not in motion. It's not driving. We just put the car on the road on this incline with ice, with no friction. What's going to happen? Well, with no friction, there is a component of force down the plane, a component of the weight, and the car would just slide down into the shoulder of the road down at the bottom of the incline. That's when there's no motion, but we want to do some motion. Before we get into the calculation, let's take a look at our diagram. It's always good to make a diagram of the problem, and we're looking here at the incline plane, the car with two headlights, and I want to think about this diagram. Our diagram should show all the forces that act on the object of interest. Does this diagram show all the forces that act on the car? The answer is no. There's a contact force between the surface here and the car. That contact force points at an angle up here. That's a normal force. So normal to the plane, a right angle to the plane, call that the normal force. And it's perpendicular to the road. It's the contact force between the car and the road. And that's going to be useful to us in solving this problem. There's a portion of the normal force that's used to balance the weight of the car. The car is not accelerating up away from the roadway. So we have a downward mg acting on the car. There must also be an upward force acting on the car so it doesn't pop up into the air, accelerate into the air. So the next diagram will have that. Another portion of this normal force will give us the required centripetal force. This car is supposed to move around a curve, a portion of a circle. In physics, when something is moving at constant speed around a portion of a circle, there's a centripetal force that's producing that motion. So let's put on the components of the normal force. One component of the normal force is mg, upward, balancing the mg downward. So these have the same magnitude. My drawing is maybe a little not to scale here, but the upward mg equals the magnitude of the downward mg here. This is a component of the normal force. And then this component of the normal force is a force directed towards the center of the circle. So we can start using these concepts. I already kind of got ahead of myself here, but the net upward force is equal to mass times the upward acceleration. If you observe cars going around banked tracks, you'll notice that they don't have an upward acceleration, so that's a 0. So we have to have that the adjacent side here to the angle, this F normal times cosine theta, that would be positive upward, and then take the weight of the car as negative. So that's, add those two forces together, this is a negative because it's downward. Those two add up to 0. So we can deduce that F normal times the cosine of theta is equal to mg. Remember, we're trying to find the theta. We're putting together some clues here to enable us to find theta. So what happens in the horizontal direction? The horizontal component of Fn is Fn sine theta, and that's equal to our centripetal force. It's supplying the centripetal force. There's no friction in this problem. We say we're on ice that has no friction. So the centripetal force is totally supplied by this component of the normal force. Well, take a look at this triangle up here. The theta is up at the top of this triangle. And you might want to convince yourself that the angle theta here is the same as the angle of the incline. I'll let you do that separately, but it is true. Tangent of theta is equal to opposite side divided by adjacent side. The opposite side is F sub c. The adjacent side has magnitude mg. The centripetal force can be substituted here. There's a formula for centripetal force. It involves the mass that's moving in the circle, the speed squared, magnitude of the velocity squared, and divided by the radius. So let's substitute that in. So tangent theta is equal to the centripetal force, mb squared over r, divided by mg. If we simplify this a little bit, divide through by the mg, it becomes in the denominator here, multiplied on the r. Think about this just a minute before I go to the next slide. Tangent theta equals mv squared divided by rmg. Well, you should have noticed that the mass will cancel here. There's a mass in numerator and denominator. So the mass of the car cancels, and the tangent of the incline is equal to the speed squared divided by the radius of our circle, and also divided by the acceleration of gravity. This is good for highway engineers. When they build a banked curve, they don't have to use a different path with a different theta, a different ramp angle for cars of different masses. Cadillacs and Volkswagen Beetles, other light cars, motorcycles, they all have the same theta. It's just one road for all masses of cars. The mass of the car does not influence the angle we should build for the slope of our curve. So we were given a posted speed limit. We want the cars to go around this icy curve at 40 miles an hour. It's just a number I selected. 40 miles an hour. Let's go into metric units. We convert by this conversion factor, 0.447 meters per second is equal to 1 mile per hour. We get 17.88 meters per second. And intermediate calculations, I keep 4 significant digits. I don't round off to 3 significant figures till the end. The radius was given in feet. We convert that to meters as well. Pause and repeat these conversions to practice doing that. Make sure I did them correctly. So let's put the numbers in. So tangent theta is our speed squared divided by the radius of the circle, also divided by the acceleration due to gravity. And I come up with tangent of theta equals 21384. Are we done? No. The problem asks for the value of theta. We have tangent theta. Well, how do we get the theta? We somehow have to remove theta from the influence of this tangent function. The way to do that is to apply inverse tangent to both sides of the equation. Again, tan with a -1 power. This is not a -1 power. It's inverse tangent. This is the symbol for inverse tangent, arctangent. So inverse tangent of tangent. These are inverse functions of each other, so we just get theta on the left side. On the right side, we have inverse tangent of 0.21384. It's time to put your calculator in degree mode if it's not there already. Pause the video and take inverse tangent of 0.21384. You're back. Hopefully you have 12.1 degrees. I've rounded off here. But the slope of this plane, this roadway, should be 12.1 degrees for the car to go around at 40 miles an hour with no friction being present. So that was a physics problem. What about in the real world? Can cars go around with a little higher than 40 miles an hour or a little lower than 40 miles an hour and not slide into the ditch on the upper side or slide into the ditch on the downward side? Is it possible to go at a slightly different speed? And the answer is yes, because in the real world there's friction. Ice is not friction of zero. There's still a little bit of friction. So we can go around a little faster or slower. And the static friction force between the ice and the tires will be in the direction necessary to keep us on the roadway. Don't test this out. It is true. Oh, for some other physics and astronomy sample videos, sample problems, and short lectures, you go to my website, gpclements.com. It's a simple website. It's not fancy. Everything here is free. You don't sign in. You don't register. You don't need a password. You don't give me any of your information. Hopefully you make use of the information that's there, and you'll find the YouTube videos listed by title, and then tells you how many minutes they go, and there's a direct link to the YouTube video at this site. You don't have to search for them on YouTube. Ask your instructor if you have questions.